Welcome back to Module 4 of Engineering Vibrations, the Introduction to Single Degree of Freedom Systems. We're moving right along in the course. So our learning outcomes for today are to take those springs that we talked about in the last module and look at equivalent spring constants for systems that have multiple springs instead of just a single spring. We're going to compare what's called parallel spring systems with series spring systems. And so here is the review from last class where we looked at linear springs and torsional springs. We're going to look at linear springs in parallel. These are springs that have the same displacement. So here's a system where I have a rigid bar down here. And that rigid bar is like a plate that's pulling down both springs. One spring has a K1 spring constant, the other has a K2 spring constant, and they're going to be, because the spring is going to be completely oriented vertically, they're going to be pulled down at the same length delta. And so we're going to change that system of parallel springs into an equivalent one spring that we can deal with in our equations of motion and the differential equations, etc. And so here, those two springs are going to come to be an equivalent spring constant. So how can we do that? Well, we can say in the first diagram, the total force is the spring force coming from the K1 spring and adding on to that the spring force from the K2 spring. And so both are going through the same displacement delta, so we add them together. Now in the second diagram, it's just like we saw before in the previous module where with a single spring, it's just K equivalent delta. Now that we have that in that form, we can cancel out the deltas and we see that the K equivalent for parallel springs is equal to the K1 and the K2 for the two separate springs. And that works for 3, 4, 5, however many springs are in parallel. The other type of equivalent spring system we can have are series springs. In series springs, there's the same force in the spring throughout. So here's a diagram of that. The force in this spring 1, since this is two springs attached together, the force flowing through all the springs is the same. It's force F. Wherever we would cut, for instance, a free body diagram, the force would be F down. Whether there or anywhere we cut it, the force is going to act down. And so it's the same throughout. So again, we want to turn that into an equivalent spring constant. And so we're just going to go with one spring now rather than two different springs attached together. And we're assuming that K1 and K2 could be different. Now, spring 1 is going to displace delta 1. And spring 2 is going to displace delta 2. So the entire displacement of the equivalent spring is going to be delta 1 plus delta 2. So here we said the force is the same throughout. So the force in spring 1 is K1 delta 1. The force in spring 2 is K2 delta 2. And over here, this force in the single equivalent spring is K equivalent times both delta 1 plus delta 2. Then we can do a little bit of a mathematical manipulation. I'm going to change K equivalent to F over delta 1 plus delta 2. I'm then going to sub in K1 delta 1 and K2 delta 2. And I get that result for the K equivalent. I am then going to cancel out the F's, and so I have, if I cancel out the F's, I just end up with 1 over 1 plus K1, 1 over the quantity, 1 divided by K1 plus 1 divided by K2. And so K equivalents on the left-hand side. On the right-hand side, if I multiply the top and bottom by K1, K2, so this would be K1, K2, K1, K2, K1, K2, The K1 cancels here, the K2 cancels here, and so I end up with K1, K2, whoops, this should be K2, right? K2 over K1 plus K2. So that's the equivalent spring constant for springs in series. Next, I'd like to do a problem together with you. So let's start with a ceiling support with a spring attached to that. And then let's go ahead and have a block in the middle. And then let's put another support spring down attached to a floor support. And we'll call the spring constant for this upper spring K1 and the spring constant for the lower spring K2. And so I'd like you to pause the video now and try to tell me whether this system of springs are in series or in parallel. And then once you've figured it out, I'd like you to come back and we'll solve it together. Okay, let's take this system now and let's go ahead and give it a deflection down of delta, this block. Okay, and so if we do that and I redraw my block, we see that the left spring will now be in tension. And so it'll be up, and we'll call that force F1, and it's equal to K1 times delta, since the spring is in tension. Now the other force from the other spring will be pushing up if the block goes down a distance delta. So it'll be pushing up. But I want you to remember back to one of my earlier courses with rigid bodies. Let's say this block is a rigid body. By the principle of transmissibility, a push up is equivalent to a pull from the top. And so we could draw this other spring as being in tension at the top. F2 equals K2 delta. And so this spring system on the left could be redrawn as a block with two springs above it. Both in tension. K1 and K2 with a delta down, so that it results in a spring force up in 1 and up in 2, since both springs now are in tension. And now it becomes pretty clear to you that these springs are in parallel, even though the first picture looks like they might be in series. But the key here is that the displacement of both of the springs is the same. So over here, even though it's in compression, we're saying that a spring in compression is linear in both the tension and the compression range. And so they both have the same deflection. If this goes down delta, the spring force in compression is equivalent to if it was in tension at the top. And so now I can write my entire force as equal to F1 plus F2. And we can substitute in for F1, K1 delta, and for F2, K2 delta. And that's going to equal K equivalent delta. And so then I can cancel out my my deltas, delta here, delta here, delta here, and we find that K equivalent equals K1 plus K2, and so the systems are the springs are in parallel, and that's our answer. So you always have to look at it more carefully than just viewing it and saying, oh, that's in series. This is an interesting case where it's actually in parallel. So in summary for this module, we've developed equivalent spring constants for systems of multiple springs, and we compared springs that are in parallel with springs that are in series and how to reduce it to an equivalent spring constant. So that's the conclusion of this module, and I look forward to seeing you next time.